Okay, people, let's start. I have one comment, which is, by the way, this is our URL where all the shit is, but that you got that in email, so I don't know why I write it. One thing that several people have mentioned, JD mentioned it last time, and is that maybe we should be building some kinds of notebooks that like embody the content of these things we learn. I love that idea, and I'm going to stop time and do that. But anyway, it's something to discuss if people, especially if there's a subject area that comes up where you're like, hey, this is important and we could write a little tutorial. I actually think tutorials like that really live. Like they get a lot of uptake. We have some tutorials on like Gaussian processes and MCMC that get just tons of uptake. So you know, if anybody wants to do something, let's do it. I will help. But I can't promise that like for every class I'll have like an associated notebook. Although one of the things we could do is we could actually work through a notebook in one of the classes. That would be fun. Like we could create a notebook and then work through it. And then we could all edit it, make it better. And then that would be a product of the class. Because one of the things I'm sort of struggling with in this is like, how are we working together? I want us to be working together on something. Anyway, so just think about that. Use your creativity. This is an experiment. I don't know what I'm doing. Good. And I was going to talk about measurement today. And then next week, I put up some potential. There's sort of a little bit of schedule at that webpage. I said that next week it's FWAM. So we'll be off for FWAM, especially since FWAM has very related content, by the way. I strongly recommend FWAM. And the second day of FWAM is extremely relevant to us. It's things like how to program in JAX with our former colleague, Dan Foreman-Mackey. And also things about like making very fast code that does fits models and stuff. So it's really useful. FWAM's very relevant. Okay, good. Okay, so I'm gonna set up a problem and then we'll, well, anyway, we'll see. I don't have that much of a plan, but here we go. Okay, here we go. So imagine you have some data. I've drawn this plot a million times. And at various moments X, I'm being a little unspecific about what X is, but at various moments X, you made a measurement Y. So the idea is that you chose your X values, like maybe these are times and you're measuring the brightness of a quasar. And these are measurements of the brightness of your quasar. So for me, Y is usually data, but it'll vary, but usually Y is data for me. And X here is not really data because you chose your times. So this might be like the times that the Gaia spacecraft crossed over a star, and like Y is the right ascension of the star when it crossed over it. Something like that. So the X's aren't really data, the Y's are the data.
In that you're assuming that you have perfect knowledge of X?
Another way to say it is I'm kind of assuming that the error bars are smaller in X. That would be another way to say it. I believe the Gaia spacecraft clock better than I believe.
Not smaller, negligible.
Yeah, like much smaller or negligible. Yeah. Much smaller is sufficient. By the way, the Adam Rees paper that won the Nobel Prize does this wrong. So the main thing you should learn here is that doing the things we learn here will reduce the probability that you win the Nobel Prize. Anyway, I just need to say that full disclosure. They actually fit the data this way in that paper. And then they were surprised that they had a bias. Anyway, long story that we're not going to think about. Okay, so now imagine that what you want to know, imagine that I want to make a measurement. So what's our measurement? Oh, by the way, there's this whole thing about measurement. Like, what is a measurement? You could mean a lot of things by measurement. This is a measurement, right? That's a measurement. But I want to talk about how do you measure something about this data set. And the weird thing about what I'm going to say is that actually this measurement probably came from some other thing that looks like this. You know what I mean? Like this measurement of the brightness of the quasar came from like an image of the quasar, and you were fitting like a point source to the quasar, and you were measuring the brightness in a set of pixels in an image. And even that image probably came from, you had some raw data and some darks and some biases and some flats, and you did some operation on those things to even get that image. So like there was some raw data that created reduced data, there was reduced data that you photometered, you put the photometry here, and now we're gonna make yet another measurement. You see what I mean? Like data is always a daisy chain. You're always somewhere in the middle of a huge chain of command, unless you work right with the readouts of the instrument, which I do sometimes. Joseph Long here does work directly with the readouts of the instrument, but it's rare that people work. Actually, with Gaia DR4, we're going to get some direct readouts of the data of the instrument, which will be really fun. Also, if you work in SDSS5, all of the data, all the way down to raw, is available to everyone on the web all over the world. So all the way back to raw. So you can see the whole daisy chain in SDSS5 if you're interested. So what I wanted, so now what I'm imagining is I'm going to assume that whoever gave me this data point did a good job with it, and we'll decide what good job is. And now So is already looking uncomfortable because I remember, I think that in the transit spectroscopy, these might be wrong. But anyway, imagine that these data were given to us by a pretty good oracle. These error bars are believable. And now what we want to know is how fast is this quasar changing its brightness? Or how fast is this star moving across the sky in the RA direction? See what I'm saying? So in some sense, what we want to know is like the slope of some kind of line. Good thoughts? How in general could you approach this? I have so many, by the way, there are so many ways you can measure this slope. There's one that I love, and it involves a formula that I write on the board over and over again, basically every day in my office, like, because it's comforting. I have a necklace that has it like this. So there's a formula that I would write down, but there's a lot of ways to measure the slope. Yes.
I mean, I would just think it's hierarchical Bayesian.
Of course you would. It's hierarchical Bayesian inference. Actually, the funny thing is, so we're going to do this, write down this really, really simple thing eventually. Eventually, we're going to get to a really simple thing. And it is going to be equivalent to a part, like the likelihood function part of a hierarchical inference. But why does he say hierarchical inference? Because each of these data points is somehow represents some kind of probability distribution for some property of the quasar. And this slope is saying, oh, these are all related in a certain way. So all the data points can be combined. That's such a funny thing to say, because that's such a funny thing to say, because this is what you do in like first year physics lab class, and no one ever calls it hierarchical Bayesian inference, but it is actually, or that is one of the solutions. That is a solution. Actually, the solution we're going to do maps very strongly out of that, but there's lots of other things you could do.
Are you saying that each point gives you a probability on the slope?
Not exactly, but yeah, well, sort of, in the sense that if you change the slope or change the offset or whatever, each data point would disagree more or less with that change. So each of them is contributing information to the slope.
But only in combination.
But only in combination.
One point gives you no information.
Right, one point gives you no information, right?
But not no, right? Like, it gives you some, right? Because the hierarchical inference is just the product of the individual ones. So if everything would give you no information, then the product would also give you no information. Right?
I actually think that might only be true if you're Bayesian.
I haven't thought about it. Okay.
I think if you come from a frequentist perspective, you don't get any information from one point. But you're right, if you're Bayesian, you do, right? Because you'd have some prior over offset and slope, and then every data point gives you some information.
Oh, okay, yeah.
Right? Yeah.
Just to bring us back to the basic
Yes.
part of basic
Super. Let's go to
measurement.
basic. Yeah, we want to get basic. That's the point. Yes, I knew it would go off the rails as soon as he put his hand up.
I know. I'm here to bring us all the way down.
Yes, good.
because
Please do.
I have no data
Please do.
experience,
Please do.
but I know how to do one thing.
Yes.
Draw a line
Yeah. Good. I
and
just
have it
drew
kind
one.
of match the things.
Yeah.
And measure how much it doesn't. So like a chi-squared.
Yes, you could do chi-squared. You could do chi-squared. That's even more sophisticated than some methods that people use. But right, you could do chi-squared. So one thing we could do is we could write down, okay, so we already mentioned hierarchical Bayesian inference, which I'm just going to call HBI because that's so ridiculous to even bring that up. And then we could do chi-squared fitting. This is a class where I try to insult everybody slowly throughout the semester. Chi-squared fitting, very good idea. That is what I would do. That's what I learned to do in first year of undergrad. We did some lab experiment with I don't know what, and then we did chi-squared fitting. But you can do much dumber things. There's way dumber things, and they're perfectly acceptable things to do. Dumber, go dumber. You're being so clever.
Kai by eye.
Kai by eye. You could just say, I didn't do a bad job. That is a measurement. You get like people like to joke like you can't do that, but that's a measurement. It's not a very good one, but it's a measurement. Yeah.
In our group, we call that old guy with a ruler.
Old guy with a ruler, exactly. I'm good at old guy with a ruler. I have many of the
We were
characteristics.
basically right most of.
I have all the things I need except a
Same
ruler.
answer if you do it with a ruler.
Absolutely. If you go back, there's an original, actually, Scott Tremaine had this funny, he gave this great talk at NYU a couple of years ago where he showed that everything that Oort said about the Oort cloud turns out to be exactly correct. And Oort didn't even have a ruler. Oort was just looking at some like.
It was the war.
Right. Yeah, exactly. They had to beat the rulers into bullets. And so he was like, he was just looking at a few random observations of like long period comets and figured out everything about the Oort cloud. And it was, yeah, not even a ruler. Good, great. That's an option. Another one that it actually works well and it's easy to analyze is you just take the first point and the last point and you say that's the change. You can see that's not going to do a great job here, but it's an allowed thing and we could analyze it. That would be perfect. Old guy with a ruler is hard to analyze, but that method is easy to analyze. Another method that's easy to analyze is you just split the data in two and you just say, oh, these data are lower than these data have an average position here, these data have an average position here, you'd get an average slope. You're allowed to do lots of things. You don't have to be all principled about how you do it. You're allowed to do simple things. Sometimes you don't need it very accurately.
Yeah, I mean, I think the metric is a lot of times like the data quality is good enough that there is, a lot of these advanced techniques show their mettle when you're in the thing where you need like a very high level of precision or you're dealing with biases. But a lot of times your signal to noise is effectively infinite. There's not a way that you could have, that your measurement errors and biases are orders of magnitude below your signal. And then, you're fine.
Right. So what does it mean to like make a precision measurement? That's a great point. And if you, so and of course even when I'm in meetings, and it goes around the room and we say our names and what we do, I always say I work on precision measurement. That's what I do. So I'm going to answer this question. How would you do this as a precision measurement? But you're going to see that the requirements for the precision measurement are really high and you don't always meet them. Like for one thing, if you want to do a precision measurement, you're going to need to know exactly what these error bars mean. And when you're in lab class in first year physics, remember, it was just like, how accurately do you think you're measuring that thing? Remember, and you'd be looking at your ruler and you're like, well, the spacings on the ruler are 1 millimeter, but I think I'm doing a little better than a millimeter. Remember that? Mm-hmm. I really remember that. And I was like, this is gross. But so, in those cases, you can't do a precision measurement because it's going to turn out, I'm going to show you why, you can't do a precision measurement unless you know exactly what these error bars mean. And those error bars were, by the way, young student with a ruler.
Not old man.
Say again?
Not old man.
No. Old man and old women are at the front of the room, and young people have the rulers now. The young people have the rulers now. Anyway, okay, good. So Great. So I think the issue, so I believe, and I'm about to say what I mean by this, I believe there's a fork in the road. And the fork is, do you have a likelihood function? And I'm going to say what that is in a second. And then subsequently, a part of the fork of the road is, do you believe it? And this is related. I referred to it last time when in the Astrofest. Remember in Astro? Well, no. I hope you don't remember Astrofest because it was like a blast of information. But in Astrofest, I said that I love doing precision measurements, but sometimes in order to make a precision measurement, you have to make a brutal approximation. You can't always make a measurement that you're fully happy with, because in order to make a precision measurement, you have to have a likelihood function. And you have to believe it. And you never do. In fact, in EPRV context that we've been working in, we really don't believe any likelihood functions that we have. We don't know what the noise sources are that are causing the jitter in the radial velocity. Therefore, we don't have a likelihood function. I'm going to say what a likelihood function is right now, but we don't have it in most cases. And that's a place where we're really doing precision measurement. We're trying to measure the velocities of stars to centimeters per second, talk about precision, but we don't have a likelihood function. And this is where extreme precision radial velocity is stuck. We don't have a likelihood function. In some ways, the group here is building a likelihood function. We don't really talk about it that way, but we could be, right? We are kind of building a likelihood function. Yeah, like all that. The depth stuff is part of a likelihood function. I think. But that's because, but you care about stars. You're like, it's about the physics of stars. I'm like, it's a component of a likelihood. That's why I got so excited when you showed this. He's figured out for stellar spectrum, what depth in the star do the different parts of wavelength come from on average and also in full distribution. And I'm like, oh my God, we need that for the likelihood function. He's like, no, it's about how stars work. But it is true that this likelihood function is partly about how the world works. Okay, so let's write down what the likelihood function is. So what you want, here's the thing. Here's what you want. Let's take this data point. This is data point yi.
David,
Yes,
could you first explain what a likelihood function is?
I'm about to.
Okay.
That's what this is about.
All right.
Okay, so this data point is some value, like has a value yi. So like this value is yi, you see? This is data point I, and that's value yi, and this is also at some like xi. So this is like at position xi, yi, and it has some error bar on it, sigma I, right? That's this error bar is sigma I. Good. And one thing you might be able to dredge up from your memories of first year physics is that a very relevant thing is 1 over sigma I squared. Remember when you do chi-squared, you sum up the residuals multiplied by this? Remember? This is, we're going to say what this is in a second, but it relates to the likelihood function. But this is usually the more important thing about your data than this. And actually, when we go on in this class, we're going to learn that this is something like the information. This is like the information being brought to you by data point I. So in answer to Gus, there is some information being brought by data point I. Obviously, we only learn this slope somehow by using them all together, or we only learn it accurately by using them all together. But somehow the information brought by one data point is more or less that. And we'll see why. We'll do information theory eventually. I think it's you that said you wanted more formal content. We will do some formal content where we see why that's the information. By the way, another way to know that this is the information is imagine you observe twice as long. So imagine this is just a stupid counting experiment, like you're just measuring photons from the quasar and you measure twice as long. You see how this gets a square root of 2 smaller. This gets twice larger. So this is the thing that grows linearly with your observing time. If you observe more, you get more information. That's why this is the thing everyone should be talking about, not that. Anyway, we haven't got the likelihood function yet. So the idea is that you want these, again, this is the requirements for precision measurement and we want to have a likelihood function and we want to believe it. The idea is that the probability that I got the data point yi, given its position, meaning given where it is in time, depends on that position, this error bar in some simple way, and or this information in some simple way. Maybe I'll be really consistent and call it the information. And some parameters that you care about. And these parameters here, these will include the slope, the offset, and maybe other terms. Maybe we're fitting not a linear model, we might be fitting a quadratic model or whatever. You know, this is whatever parameters we're fitting. There's some parameters. And if we can write down this function, and if we believe it, then we're in a position to make a precision measurement. Otherwise, you can't really make a precision measurement.
So that's the likelihood function.
This is the likelihood function for point I, and then we're going to multiply together all the other points. And sometimes people get confused here because they think, well, I'm trying to figure out what are the properties of my parameters given my data. Whereas this is what properties do I expect for my data given my parameters? Why is it this thing? One answer is trust me. Good snort. Of course, Bayesians believe that the goal is to give you the probability of the parameters given the data, but we'll talk about that eventually, but in Bayesian inference, you start with priors and you end up with a posterior, and you get from your priors to your posterior by multiplying in the likelihood function. So the likelihood function is the thing that contains all the information about your model. This is it. The prior that people have is some other subjective input that is additional to the information about that the data are bringing. This is the sufficient thing. This brings all the information. If you know this, you know everything you need to make a precision measurement. This is it. This is the only thing you need. But you need it, and you need to believe it. Good? Great. And then the total likelihood, then there's a notational thing that I will sometimes write, but it gets really burdensome, is that really what you want is the probability of all your data. Let's imagine you have n data points. This is like the set. Sorry, by the way, Apple does this. I looked it up on the internet. It is impossible to stop it. You cannot stop it. There is literally no setting. I need a different app. I need to switch apps. Say again?
Good notes.
Good notes. That's what I should use. I will have it by next week. This is like the set of all the data. I goes from 1 to n. This is like a set notation. It's a useful notation sometimes, but sometimes we just replace this whole thing with like a capital Y to say like we're putting it all into one object. And there's going to be a bunch of notational choices here that are a little annoying. But anyway, this probability for all the Y depends on a bunch of information you have about the problem and then your parameters. And this information that you have about your problem includes all the xi's and the sigma i's, or 1 over sigma I squared, I should say, from I equals 1 to n, but it also includes all your assumptions. And we're going to make a ton of assumptions if we can get there. So the idea is that there, you have parameters of your model. Everyone focuses on the parameters, right? Your likelihood function has parameters. You have some parameters, but there's also a hell of a lot of assumptions you're making. Oh, I'm assuming it's a straight line. Oh, I'm assuming, and in a moment, we're about to assume that the error bars are Gaussian and that we know their uncertainties and all that kind of stuff. We're going to make a ton of assumptions. So your model, there's always a thing you're conditioned on. Bayesian's like this. There's no unconditional probabilities. There's always condition. All probabilities are conditioned, and this one's conditioned on a whole bunch of beliefs about your problem. And those beliefs include like that we know these xi's exactly, which is, remember, I opened by saying, let's assume we know the xi's exactly. That's one of the assumptions in here about these xi's. And we're going to assume these error bars are correct, and we're going to assume a bunch of other things. People good? Okay, good. So now this probability is, imagine that in many cases, by the way, people always talk about correlated noise and correlated whatever, and people get really nervous. I'm about to make a move that makes a lot of astronomers nervous, but it shouldn't make them nervous. If you have taken images of a quasar over time, you took images of a quasar over time, those images have completely different noise properties every time. It's a different, like literally the gods of quantum mechanics guarantee you that your noise in each image is actually uncorrelated. It's like required by the laws of physics that you have an uncorrelated noise. Now, you might also have some small correlations in the noise because there's things like flat fielding of the imager or something, or calibration that you don't understand that maybe correlates them. But often it is not a bad assumption to assume that this measurement is truly independent of this measurement. It's different photons. Sometimes these were taken with different devices. You know, this might have been taken with Ys and this was taken with JWST, like that's allowed. And then they're really, really independent measurements. They're like different hardware, different photons, different times. It is not uncommon that your data are truly independent. Yes?
But I mean, even if the device is different and different photons, like if the weather is similar, that surely, like in principle, right?
Yeah, it is true that there are a lot of things that can correlate your noise, your error bars or whatever, correlate your data points, but many experiments are very safe, extremely safe. So for instance, in Gaia, there's been a ton of work in Gaia to figure out how correlated, you know, Gaia sweeps over the stars, ton of work to figure out how correlated they are because there is an overall instrument model. And the correlations are incredibly small, like far smaller than the error bars. So it is extremely good assumption in Gaia to assume that every crossing of the star is an independent measurement. And it has to do with the fact that there's so much data constraining the instrument that they get uncorrelated. But anyway, we are about to make so we're about to make an assumption. So remember, like, just keep track of some assumptions. One assumption is we've assumed that we know that these xi's exactly. Another assumption we've made is that it is possible to write down a likelihood function given this information, which kind of means that these error bars aren't like, you know, students with rulers, because we don't know how to write down a probability distribution for students with rulers. If we did, that would be really great. I'm now about to make another assumption, which is this independence assumption, which is that this can be written as a product from I equals 1 to n of all the individual yi's. And I'm just going to do I comma theta because this I here summarizes the information that's here. So meaning the probability of the whole data set is just a product of all the individual probabilities. Good? Everyone's good? But this is a strong assumption here. So if you're counting assumptions, we should be counting assumptions. I guess I should highlight assumptions. Like there's an assumption here that we assume that, whoa. Oh no, now I have the wrong kind of eraser on. Everything's gonna die. please do that. Thank you. Good. I was going to do this. We've made some assumption about X. We've made some assumption here that you can write this thing down. And now we've made an assumption here that you can make this equal to that. I'm just highlighting assumptions here. There's going to be so many assumptions. It's ridiculous. And you're going to be like, after this, you're going to be like, I don't believe any data analysis I've ever seen. Because this is the dumbest problem you could ever do, this problem. And it's so many assumptions. It's going to get worse before it gets better. So now, if we are going to actually come up with a mechanism, so first of all, we have a likelihood function here, and there's many things you can now do with this likelihood function. One of the things you can do with this likelihood function is, is you can optimize it. And then you get the maximum likelihood. What do I mean by that? You do argmax, here's some notation, argmax over theta of P of data given theta. So if you maximize this probability for your data given your parameters, that's the maximum likelihood. And this estimator has extremely good properties. If you can get this estimator, you should. Even if you're a Bayesian, you should get this estimator and publish it alongside your far more expensive Bayesian inference. Because this has better statistical properties for some of your users than your downstream, this is a very good thing. Do this. I think everyone should always do this. If you can write down a likelihood function, optimize it. Why not? It also gives you a good starting point. If you're going to do all your crazy MCMC, you get a good starting point by starting here. Now, the flip side of that is optimization is hard. Sampling's easy, optimization is hard. Yes?
Why would you ever like not optimize it? Like, or
You
I've never seen that, I feel.
mean why would you do something other than optimizing it? Well, one reason there's sort of two reasons you might not optimize it. One is, and this is the reason I often don't optimize it, is I just can't optimize it. Like once this thing gets big, sometimes you just can't afford to optimize it. It's too expensive. Or there's too many parameters. Like once this gets to be thousands of parameters, it can be really hard to do. Another thing is, this problem is going to be super simple, but some problems aren't simple at all. So like in the Yoker, do you know what the Yoker is? Where we look for periods in the apogee data. Every apogee star produces like 100,000 or something peaks in the likelihood function. Like every star produces tons of peaks in the likelihood function, so you literally can't find the top peak under any circumstances. Even though you only have 6 parameters, you still can't find the peak, or not with a finite amount of code. You know what I mean? So that's one reason. The other reason not to optimize it is you might be Bayesian and you use it to create a Bayesian posterior. And the Bayesian posterior some people want the probability of the parameters given the data, and that is equal to some normalization constant, which I despise, times the probability of the parameters times the probability of the data given the parameters. So meaning in Bayes, this is Bayes' rule. In Bayes' rule, you have some prior beliefs about the parameters, and by multiplying those prior beliefs by the likelihood function and then renormalizing, you get a probability distribution for the parameters. And first of all, if you're Bayesian, often you want this. Although I think Bayesians often want something else and are slightly wrong, but whatever. Some Bayesians believe that they want this, and that's good. And then the related to this is this thing is what you sample with MCMC. So and one of the reasons, by the way, this is my fault. not my fault. It's partially my fault. Partially my fault that the astronomical community uses MCMC so much. And I take the blame and I'm hereby apologizing. But people use this because it's easy. We built really good tools for this. It's really easy to do. Optimization can be really hard to do. So oddly, it's easier to be a Bayesian these days than to be a frequentist. So I think one of the reasons people don't optimize it is they just multiply by a prior and put it into MC and it works. End of story, which is a good thing to do. I mean, or a terrible thing to, I don't know, I'm embarrassed. It's what people do. I'm sad about it. But we got 15,000 citations. Yeah.
Presumably you look actually at what the maximum value is, right?
Like, good.
Like if the maximum value is like 0.1%, then.
Good.
Well,
Notation here. So what I wrote, good. I'm stepping back for a second. I wrote argmax theta. What do I mean by argmax? But by the way, that says argmax. Just FYI. Anyway, and there's no LaTeX symbol for argmax. You have to make your own. You have to declare math operator with a star on it. We should have there'll be a session on like how do you typeset the data analysis expressions. What do I mean by argmax? What I mean is we're not getting the maximum value of this function. We're getting the parameters that deliver the maximum value of this function. It's the argmax.
Yeah.
And then the question is, what about the value of the maximum? Is that useful?
Yeah.
And there's two answers to that. One is yes, and the other is no, and they're both valid. The no answer is we're about to write down a likelihood function, and there's like a constant term that we usually throw away because we can't stand it. And you don't need it, but that means then the values you get aren't actually your likelihood. But then the yes answer is in chi-squared fitting, there is a meaning to your chi-squared, which has something to do with whether your model assumptions are correct. Remember, we're making tons of assumptions. Every assumption we make, we want to test. Oh, by the way, important point. When you're making assumptions, you're not saying, whatever, just going to do this and then take off. You're writing down a list of assumptions you made because you're going to go back and look at whether they're true. Yes.
So the priors, the P of theta, this would be like if I said, I think that the slope is between 2 and 2.6, and I think the intercept is between something.
Exactly. It would be, and if you're looking at a quasar varying, it's hard to have prior beliefs. Like I just don't have any prior beliefs about where the quasar is doing and what it does. Now, maybe if I'd looked at a ton of quasars in my life, I would start to have prior beliefs. But right now, I don't have any prior beliefs. So that's one of the many reasons that I like maximum likelihood, because maximum likelihood has very good properties, and I don't have to decide what my beliefs were before I started. But technically, if you want to be a proper Bayesian, you actually have to have beliefs. You have to have a belief about what quasars do, which is a hard lift. I have things to say about that. There's a whole, actually, probably eventually we'll have some conversation about priors, because most people in this room have priors and struggle with priors, and priors are a problem. They're very problematic for a lot of reasons. Was that a question?
I'm satisfied.
Okay, good. Okay, good. Now I'm going to write down a possible form you could assume for this probability. By the way, whenever you're doing, by the way, there's a red flag on the board. There's a red flag on the board. There's certain things that I consider to be bugs in code. Like in later, where I'm going to tell you that the inv operator that takes the inverse of a matrix is a bug. If you ever have inv in your code, you've made a mistake. There's a better thing you should do that's more numerically stable than inv. Similarly, if you ever have prod in your code, you have a bug. You never want to product a lot of things. Why not? Because you get underflow. Basically, if you product enough things, you will always get 0. So don't prod. So what we're gonna do is we're gonna sum the logs of these, and we're always gonna work in logs. So let's write down the log. And for me, the log is always the natural log. By the way, if you write this, for me, log is ln, and I'm gonna say ln, and I will always say ln, and I learned last year, I've been teaching for an extremely large number of years. And last year, the students made fun of me for saying ln. So I learned last year that nobody calls that ln. Who here calls that ln? Where did you grow up?
So many logs there, they're beautiful.
Exactly. Get off of my lawn. That's what you heard that all the time. No, I believe it is possibly a Canadianism to say lawn. Do we have Canadians in the house? No, so no one can refute that. I mean, Connecticut is kind of getting close to Canada, but there's still like Vermont there.
A lot of other things in between.
There really are. Anyway, I call that lawn. What do you guys call this? LN. So you use 2 syllables? So this is called Ellen. It's the only function with a daytime TV show. Actually, does she still have that show? I don't even know. Anyway, okay. By the way, if you write this in AppJ, they reject it. And if you write log base 10 in AppJ, they also reject it. In the AppJ, I know.
What?
Wait, no. I'm sure I have log base 10 in AppJ.
I would like to see it because every paper I've written this, they've typeset it away to log.
Oh, we need
And-
to
Have I
fight
just
that.
not been
We need to
checking
fight
the-
that.
I know, we have to go, because maybe you haven't been checking it, maybe you haven't been checking your final typesetting, because I am, so the funny thing is, so AppJ uses ln, AppJ does this. They use ln and log for these 2 functions. And this upsets me deeply because in this computer science literature, people use this for this.
Yeah.
And so our papers become unreadable in the computer science literature. It's very bad.
I mean,
We must fight. Well, I think it should be it should be CCA where we typeset log base.
No, but the thing is, these are journals of our professional society. And
Yeah.
so like, there are people there who are responsive.
They are,
That
they
we can
are.
write about
No, they are.
changing
They
the
are.
norms.
Actually,
and that thing. So like,
yes.
And be like,
Yeah.
yo.
yeah,
No,
no, exactly. Like,
Yes,
they're
I endorse.
Like rather than just sit here and get
No,
mad.
believe me,
there's
I write to them
message.
every time. I write to them every time. But no, but they are good, actually. The journals, ooh, you got a log 10 in one of your papers? You have a log 10? Are you an AppJ?
It's just
JS.
AppJS, well, no, seriously. No, that was a joke. Okay, good. Maybe the many emails we've sent have started to soften them up. Actually, I have to say, WS Journals is great. It's one of the very best things about our field. The people who work in journals take it really seriously. They're great. I think they're excellent. We have more responsive publishing than any other society, like academic society in the world. Like, and they're better than the European journals. They're better than other fields. The AppJ and AJ are really well run.
Yeah, they're not exploitative.
They're not. They're not. And we do pay page charges, but you're at the Simons Foundation, so bring it on. Okay, good. So we're gonna now make yet another assumption. We're gonna say that the log, remember, I want to change this red flag into a sum. So I'm going to talk about the log of this function. So we're going to assume that the ln of P of yi, given the information and the parameter, or given the assumptions and the parameters, is a Gaussian, the log of a Gaussian, which looks like this. Let me not be wrong. It is -1/2 ln sigma squared minus 1/2 yi minus some prediction. We're going to say what this is in a second. Squared over sigma I squared. And I think I lost a 2 pi. I think there's a 2 pi right here. It's bad to write out formulas. Okay, good. In class, my students are always like, can you just write out the formula? I'm like, no, you can look it up in the book. They don't like that. I think I got this right? Am I right? Andy's nodding. This is the log of a Gaussian. What's a Gaussian? It's e to the minus a quadratic, right? It's x to the quadratic. Here's your quadratic. It's the data minus some prediction of your data. We have to say what this is. I haven't said what that is yet. And then over sigma squared, this is, oh, look at that. That's chi-squared. That's your favorite chi-squared. And then there's some normalization constant out front, but notice the normalization constant only depends on the uncertainty. It doesn't depend on any of the properties of our model. The model's all going to come in here. That's why that's got an M, because it's like model. Yes.
That's also the slope of your line and the
Oh,
slope of
shit.
the line. Yeah.
God damn it.
Should we rewrite it to S?
Stop making like sensible points about notation. Okay, fine. What are we going to call it?
Function.
You,
Fi. Love it. Good.
One other thing.
Yeah.
Do you think it would be useful to say, instead of just saying we're writing this out as a Gaussian, do you think it would be useful to say why you say it's a Gaussian and it's because of
Yeah.
your, yeah.
Yeah. What we're assuming. So first of all, let me make a tiny change over here, which is let's remind ourselves that this is going to depend on our parameters. And then what are we assuming? What we're assuming is that in some sense, what we're assuming is that gee whiz. No, I don't want that. Stop it. God damn it. It thinks I'm trying to select something. Yi is drawn from a Gaussian. By the way, for me, Gaussians are always capital N, which is really bad because I just used the capital N. So I'll make it curly. It's a Gaussian which has some mean, which is going to be Fi of theta, and some variance, which is going to be sigma I squared. So what we've assumed is that there's a very deep assumption in when you have a likelihood function. The likelihood function, remember, it's a probability for your data. That suggests that you could have gotten different data. By the way, this is one of the places where the frequentists and the Bayesians disagree. For the frequentists, you really do imagine a world in which you got different data. You imagine that you ran the experiment over and over again and you got different data every time. And so the frequentists think of this as a frequency distribution, meaning if you did the experiment many times, you would get different data. Whereas the Bayesians think of this as a kind of confidence. It's more like confidence in the data, like what probabilistically do you know about the parameters given this data point, or how is this data point deviant from its expectation, or something like that. There's a slightly different meaning for this for the different groups. But is this what you had in mind, Andy?
Yes, that you've got some belief about the uncertainties, and therefore, if you have some belief about how the uncertainties are distributed, you've got your likelihood.
Good, great. We're assuming that the data are drawn from a Gaussian that has the variance that's set by those error bars, and that the mean of that Gaussian is set by our model for what the data could be doing. And we haven't even said what our model is. Look at all the assumptions we've made, and we still haven't said what the model is, you see? Yes.
What Andy just said.
Write it down.
What are we? Sorry. Words.
God damn it.
Sorry, what did we assume? What, no, sorry, Andy.
Good. What do you think we've assumed? Andy, state what you think we've assumed.
So a lot of people say like, why do we just say it's a Gaussian? Like, where does that come from? And it's because like we have some belief about the data, and that is that the uncertainties in the data are distributed like a Gaussian.
Okay.
And so if you believe that, then you've got your likelihood function, and everything else then it follows from that. But sometimes that's not true. In X-ray, it's Poisson distributed, right? You count the Poisson and then
that's,
you've got a different function. And so
by the way, Andy's reminding me that sometimes when I write down a model like this, I write it like this, that yi is fi of theta plus epsilon I, and epsilon I is drawn from a Gaussian, which I'm writing like this now, with 0 mean and sigma I squared invariance. So I say that the assumption is that the data point you get is created by your model of how quasars behave, plus a deviation, and that deviation is just a noise draw, and that noise draw is Gaussian. And by the way, people like to make fun of this, and they say, oh, you've assumed everything's Gaussian, whatever. But actually, a lot of things are strictly Gaussian. Like in the Planck instrument, the noise in the Planck instrument is strictly Gaussian. It's a thermally excited thermal device measuring a thermal background. It's like literally Gaussian. Yes,
Yeah.
except when it isn't.
Something else I do like about this notation is that it's very extensible to like adding in systematics.
Yes.
Like you can add another term, so you can say that I've got fluctuations up and down because of the number of photons that happen to land in
Right.
making my measurement. But I could also have things where I measure it high because that's on a place where the chip is less responsive than some other part of the chip.
Very good. Like the Wobbly model that Megan Bedell built is written in the paper like this, except there's a term which is the star, and then there's a term which is the atmosphere, and then there's noise.
Yeah, this extends very nicely both on
Yeah.
the functional piece
Yeah.
and the additional.
So
measurement.
my papers generally say these days, fundamentally, the model is this. And then we assume that these are drawn from this, and then the form of this is a linear function. And then we start by saying fundamentally, this is the assumption. Yeah.
But like there are models where it's multiplicative and so on, right? Like,
Yes.
This is a really important assumption. That's
Yes.
always,
Oh, yeah. Good.
Okay.
Great. Excellent. Excellent.
when we had a project starting with ALMA data and the visibilities, and then the first question that took a long time to get through was just like, what do you believe about how the noise in the visibilities, the complex visibilities are distributed and why? And that took like a long time. So we didn't even get to like anything about how to model. It was just talking
Absolutely.
about what do we think about the noise. Yeah.
Absolutely. So like there's really two assumptions here, as you've correctly identified. One is that things are Gaussian distributed, and the other is that the noise is additive. And you're also kind of assuming it has 0 mean and additive. So like a ton of things have been assumed at this point. Like we are deep in assumption land now. The cool thing about it is if we make these assumptions, we get to write down the best equation of all equations in all of physics. It's not E equals MC squared. That's what my students think is the best equation in all of physics. By the way, one of the things that's super cool about this is that because the Gaussian is in the exponential family, when you take this logarithm of it, you just get a polynomial expression here. See, this is, I mean, you can ignore this part because our parameters theta only appear here, but you see this is just a polynomial, it's quadratic. And that means that when we are optimizing our likelihood function, we're going to just be optimizing a polynomial, and we can optimize polynomials analytically. So there's going to be an analytic solution to maximum likelihood in this problem. You can already see it's about to happen. But we're probably not going to get there before 6 minutes from now. Yeah.
Can you give an example of a noise that's multiplicative, not additive?
Yes. For instance, there are devices whose sensitivity depends on temperature. And so if the temperature is fluctuating in the device, the gain of the device is fluctuating. So a kind of example of that is, in JWST, when there's a persistence in JWST, and the persistence is not adding to your signal, it's multiplying your signal. And so if the detailed photon noise in the previous exposure affects the sensitivity of the pixels in the next exposure because of some charge traps. It's actually not understood why, but it does. I'm sure there's lots of other examples. Amplifiers.
Maybe even your eye, like maybe the noise you have in the environment, like that reacts on, the lens of your eye, and then in principle that changes your data distribution as well. Like, I think it's more like usually it's just a convenience that it's additive, and in general probably a lot of things are not additive, but it's a very good approximation.
For some cases, yeah.
Or if you're using a gimbal to like move in some object and trying to figure out what your position is, the error integrates over time, right? And so it's like multiplicative by the time. That's why like eventually you have no idea where you are. And so it's a totally different situation.
Yes, like if you dead reckon with your phone, it like exponentiates off of the correct trajectory. Thought. By the way, actually in Megan's Wobbler is an interesting case because the atmosphere multiplicatively affects the star. So we take the log of the spectrum of the star so that the star and the atmosphere are additive. But then, of course, since the noise was Gaussian in the original case, it's not Gaussian in the new case. And so the model we built that's called Wobbler is actually only appropriate at high signal to noise, because it's only at high signal to noise that the log of the Gaussian that we took looks like a Gaussian. So like sometimes in order to, sometimes there's a, by the way, this additive noise thing is such an important point, because when I was saying like you have to make brutal approximations to make a precise measurement, you really do sometimes have to make brutal approximations. And at some level, you have to just quantify how bad your assumptions are. Because if you actually made weaker assumptions or made a more general thing, you just wouldn't be able to operate or compute it. Like a lot of things we'd like to do, we can't compute. There's no likelihood function for JWST imaging, for instance. It's just no one can write it. We don't have a mechanical model for how JWST works. So everything's an approximation. And then you just try to track how bad is the approximation, and you try to propagate through how bad the approximation is, and then you add this systematic error term at the end, which is about all the bad approximations you made. Let me say one more thing, which is that, let me say one more thing because we will now run out of time. So now imagine that I think of this data set here that I have I. Let's imagine I call this capital Y, and I think of it as a list, Y1, or a vector, Y1, Y2, Y3, ... to Yn. And technically for me, vectors are always column vectors, so I'm going to put a transpose on that. So meaning you have a column vector Y that is the list of all your data. Good. Then the chi-squared that you write down, chi-squared, remember, is the sum over I of yi minus fi of theta squared over sigma I squared, can be written in linear algebra form as y transpose dot c inverse dot y. No, dot f. No, sorry, this is just totally wrong. It's not even close to right. You can write this as y minus f transpose C inverse y minus f. See what I've done? So what I did, I have this column of data. This is a column of data. This is a column of the predictions for the data. And here it is again, it's a quadratic form. It's the square of this and this. It's like the dot product of this and this. Remember when you take a dot product, you just sum up the squares of the elements of the matrix, remember? X squared plus y squared plus z squared is the dot product between the vector and itself. So this is like a dot product of the vector in itself. That vector is this. This is the list of all the predictions. This is the list of all the data. We're taking this dot product, but we're taking the dot product through a metric, which is these informations. So we're doing the information weighted dot product of the residuals with themselves. You see how you can write this expression like this expression? Let me add one more thing, which is C is 1 over sigma 1 squared, 1 over sigma 2 squared, dot, 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 1 over sigma n squared, and zeros everywhere else.
Isn't that C inverse?
Sorry, C inverse, thank you. So this C inverse is the list of all these uncertainties on the diagonal. And now have you got it? You with me now? And now you can think of, if you have to do this transpose, you're like, and then you do, and then you get exactly this expression. Notice this is another red flag on the board. Don't ever make this thing, because you see how this thing is almost entirely zeros. Don't make matrices that are almost entirely zeros, so don't do this. But conceptually, it's very useful to write it this way. It's not a good idea to put in your code this way, but it's very good to write it that way. And we've run out of time before I write down the most important equation of all of physics.
You should just write it down.
Just write it down. I agree.
Okay, so if you have that, we would still have to make one more assumption. There's one more assumption you have to make, which is that F is some design matrix times your parameters. So this assumption is that your model is linear, that your predictions are linearly related to your parameters. That is true in this case. In the case that you're fitting a straight line, it's just got a slope and an offset, which are linear parameters. So if you make this additional assumption, how many assumptions are we in? We're so many assumptions in. So now I'm making one more assumption that it's linear. If I make this assumption, by the way, this thing is called the design matrix. And then it turns out, and we will explain why next class, the maximum likelihood value of the parameters is X transpose C inverse X inverse X transpose C inverse Y. This is the most important equation in all of data analysis. This is linear least square fitting. Even nonlinear problems, when you get close to the optimum, you can linearize to this form. This form appears everywhere. This is also in mathematics called the pseudo inverse of X. So X is a rectangular matrix. It doesn't have an inverse. This thing is the best generalization you can have to the inverse of X. It's all sorts of things. There's so many beautiful things about this expression. That's why I love it. But one of the coolest things about it is the data only appears here. You see, you just apply this crazy operator to the data and it gives you your parameters. How did we get this? We'll find out next time. But fundamentally, this is a quadratic form. We took the derivative of it and set it to 0. Remember in high school, when you found the optimum of a function, remember you took the derivative and set it to 0? Andrea, you have great command over the early days of your education.
Oh,
I like it.
Because I started over in beginning algebra when I was 30.
You see, I think it would be good to redo things later. And that's a good idea. Anyway, if you take the derivative of this and set it to 0, you get this expression. We will see that next time, but it's going to come up again and again. It happens all the time. Bye. Go, live your lives. Be productive members of society.